Okay, well, I finally got those example problems up on D2L yesterday. But so the problem we did in class on Wednesday and the one we did Friday, there's solutions up on D2L. And the way the final solutions are given, I calculate the loads, from the matrix, but then I also show them in like free body diagrams. So I like added all the forces together at each individual point, which is, I won't always ask you to do that or anything, but that's probably the most useful way to show the solution of a structure. And I also didn't assign the homework from Wednesday until last night. I forgot to do that, but it's up now. But I'll take that into account when I assign problems for today. But we're just still working through the rest of the structures. After Wednesday's or Monday's assignment, I guess there were 5 problems left, I think. So just working through those little by little. So today, this is the last day that I'm planning to talk about structures, although, I'd be happy to answer questions about it. But I want to talk about the truss simplification today. So it's a 1 day only, and I would rather, if it were all up to me, I would totally avoid it, but it's something that other people like to teach, so I want you to at least understand what they're talking about if it comes up in your later classes. This is structures. This is the end of structures. It's the simplification that is often used, often taught, and they spend a lot of time on in other classes, but I don't spend really any time on it.
Just an alternative to what you showed.
It's not it's kind of, but it has a lot of, basically it's a much faster way to do a very small number of structures. It doesn't, not very many structures fit its requirements, but if one does fit its requirements, it's a lot faster because you don't have many equations. You have a lot fewer equations. And practically speaking, it's not even if you're going to use it, it's not hugely important to know how to do it mathematically because you can Google truss calculator and it'll ask you to, you'll go to things that'll ask you to punch in the coordinates of the joints, punch in the forces, and it'll spit stuff out for you. So, but okay, so the truss simplification is based on 2/4 members. Every member in a truss must be a 2/4 member. Okay, so what's the deal with 2/4 members? So imagine you have, some arbitrary object, okay? And 2 force vectors act on this body. And the body is in static equilibrium. What can we say about the forces? That's true. That's the first important thing that we can say about it. Okay, so the first thing is, so imagine, one force this way and one force this way. So those are the two forces. Well, that thing is going to accelerate because those two forces don't offset each other, right? So there's going to be some net force, non-zero net force. And if there's a net force, there's an acceleration of the center of mass. Okay, so the first thing we can say is the two forces must be equal and opposite. Okay, so this isn't going to work. What about this? So let's say at this point here, we have another force like that. Is that in static equilibrium? It won't accelerate, but it is going to have an angular acceleration because those two things are a couple now. Okay, so if you apply a non-zero couple to something, it's going to rotate. And so the second requirement is those two forces must act along a single line. Okay, so this isn't going to work. But this could. Those are supposed to be the same magnitude. Call that F and call that F. Okay. And so what that means is you can treat two force members like they're in, basically like in tension, So you can treat two force members like a cable. So we'll assume that they're in tension because those forces just have to be in a line, just like a cable, just like forces in a cable. But the cable tensions, put that in quotes because they're not really cables and it's not really like tensions, but those cable tensions can be positive or negative. With a cable, all it can be is tension. If you try to use a cable to provide, try to put a cable in compression, it just folds, right? It can't be in compression. But a two-force member that's rigid can be in tension, or it can, like this one is, be in compression. Okay, so with a cable, if you calculate a t-value and you get negative something, something went wrong. With a two-force member, you can get negative, and that's fine. Okay. Okay, so if a structure is made of entirely two force members what you're going to do is isolate each joint as a particle. Treat each member as a cable, except the tensions can be positive or negative. Question?
Yeah, is the negative tension that for compression?
So yeah, with a cable, you can't have any compression. With these, you can have compression or tension. Hopefully, when I give an example, it'll be a little more clear what I'm talking about. But for now, I just want to get all this stuff in your notes, sort of like a definition. Okay, so how many equations are we going to get here? Well, remember that the sort of basic story is in 2 dimensions, every rigid body that you isolate, and we treat every member as a rigid body the way we're doing it in this class, gives you 3 equations, right? If you're doing it this way, every member is just a single like cable tension that you're looking for, and so every member is 1 equation. So you can imagine what a big difference in the number of equations and variables you can get when this applies. Okay. Okay, so it saves a lot of equations when applicable. Okay, so let me do an example. This is, very similar to the examples that we've been doing. So let's say there's a pin joint on the lower left and an equilateral triangle. And there's a pin here, down at the bottom, those 2 are connected by pins. Okay. And let's say that there's 200 newtons of force applied up here and 500 newtons of force applied here. Okay. Solve this structure. And I need to give you some length. So let's say it's an equilateral triangle, and each one of those members is 1 meter long. Okay, so if we're using the approach that I've been teaching for the last week or whatever, then one by one we go through the different bodies, isolate those as rigid bodies. But with this, we're going to isolate the pins at the joints. Okay, so let me label these. I'm going to call this body 1, body 2, and body 3 in the joints A, B, C. Okay. And since the pin at each joint is, we're going to treat it like a particle, we can use Newton's second law. You know, all the forces acting on it have to balance. So here's a free body diagram of pin A. Okay, so there's the pin. What loads are acting? So first, there's a reaction from the ground, so I'll call that RA. That's a full force vector we don't know, just like we would treat it in our problems. And then now we're treating this member 1 like it's a cable, right? So there's this tension force coming from member 1. I'm going to call it F1 instead of T1 because it can be positive or negative, but basically we're doing it exactly the same as if there was a cable between joints A and B. And then there's also one of these cable tensions coming from member 2, so I'll call that F2. Bless you. Are you with me on that? Okay, so Newton's second law says RAX, RAY plus, these are all 60-degree angles, so this is 0.5 F1, 0.866 F1. That's cosine and sine of 60 degrees. And then F2 is in the positive x direction, so F2, 0. And that's equal to zeros. Those are our first two equations. How come I didn't draw out the table for this?
Because it's all one point is over the origin.
Yes, exactly. Because we're treating this like a particle, and with particles, you don't use the moment equation. And so the table is really only for doing rigid bodies. Yeah. Okay, so now we're going to go to joint B. And up there, what forces are acting? Well, there's like this sort of pretend cable tension coming from member 1, cable tension coming from member 3, and then there's the downward force of 200. We're going to treat these like these forces are always going away from the member because we want a positive value to be tension. So this is the direction that these forces would be drawn if those things were cables. This is F1, this is F3, and then we have the downward force of 200. So Newton's second law for this one says 0, negative 200. Plus negative 0.5 F1, negative 0.866 F1. Plus positive 0.5 F3, negative 0.866 F3. Is equal to zeros. Are you with me on that?
Wow.
Using what? That's on a different joint still. So we didn't use any constant on this one because nothing's applied to that one. We used the 200 on this one.
Oh, they're going for B.
For B. Yeah, that's right. So now we're going to isolate C, and we'll have the 500 on that one. Okay, so what loads are acting on pin C? There's the fake cable tension for member 2, fake cable tension for member 3, the 500 newtons, and then the reaction load for that roller. So here's the 500. A roller applies a force that's perpendicular to the surface of contact toward the chosen body. So this, I'll call that RC. And then we have the cable tension going this way from member 2, was that? So here's F2. And then we have the tension for member 3, so that's F3. And notice that since, body 2 is going to have, just like with a cable, it's going to have the same tension the whole way along its length. This F2 is the same as the F2 we used in the other equation, And then so Newton's second law says negative 0.5 F3, positive 0.866 F3, plus negative F2, 0, because that arrow is pointing in the negative x direction, plus 0 RC, plus 500, 0, one, two, three, 4, that's equal to zeros. Okay, so now we have 6 equations, right? The x and y for each one of these, 1, 2, 3, 4, 5, 6. And for variables, we have RA, F1, F2, F3, and RC. 1, 2, 3, 4, 5, 6. Okay. So 6 variables, 6 equations. And you can solve that with reduced row echelon form or whatever. What we get in this case is RA is equal to negative 500, positive 100. RC is 100. F1 is negative 115.5. F2 is 558 positive. And F3 is negative 115.5. So what this means is for body 1, we learned that that's in compression with a magnitude of 115.5 newtons. So the free body diagram of this looks like this. Body 2. F2 is positive 558. So that means that this is in tension with a magnitude of 558. And then body 3 is the same as body 1. It's not very surprising because the symmetry of this thing. Negative 115.5, that means compression. So these forces are toward the body, 15.5. Okay. That is not the most dramatic example of how many equations this method can save you, because this doesn't have a ton of members. And so notice that we had to solve for this, a system of 6 equations for 6 variables. If we had done it the full way, the way that I like, it would have been 9 equations for 9 variables. So that doesn't sound that extreme. But remember that those reaction loads from the ground are the same for whatever method you use. So 3 of these 6 equations are just calculating those reaction loads, okay? So if you had 100 members, using this truss simplification, if it was applicable, you would have 3 equations and 3 variables for the reaction loads, okay? And then you'd have 100 variables for the members. So you'd have a total of 103 equations, 103 variables. Using the full approach, you just have 100 members, and you're treating each one as a rigid body. So 3 equations for each one. So 300 equations, 300 variables. So that's a big difference, Okay, so what are the drawbacks of this approach?
It's now trust due to trouble.
Yeah, you can't do it if it's not a truss. So this 2/4 member simplification requires these things. So let's say all 2/4 members means all joints are pin joints. No couples can be applied anywhere. No forces can be applied anywhere but at the joints. And then last, which really is just a subcase of number 3 here, the members can't have any weights. Because that would be a third force on the member, and then you can't make that assumption. Okay, well, the no member weights is pretty much, that seems like it's sort of the end of using this method. But that's a reasonable approximation in a lot of cases where the weight of the members is very small compared to the forces that this structure is supporting. And so, it's never technically true that you don't have weights, but often you can get good approximations, good results by treating the members like they don't have weights. Okay. And then the other one, so here's some, let's see. So here are some examples of similar structures. That can't be solved as a truss. Okay, so the first one is everything the same. But each member has a mass. Second one, that 200 Newton force is just applied somewhere other than one of the joints. And a third one would be like where this is a rigid, like fixed joint connecting this body to the ground. All of those things make at least some of these members two force members, and then you can't use it. Okay, let me show you sort of a way that might be more useful. Yeah.
Would it work without the 200 at the top?
No. Would it? Yes, I guess it would be, just because that force goes through so the reason that this doesn't work just generally.
No, like the original one. If we took the 200 force away.
Mm-hmm. Yeah, it would work. Yep. This one, just no 200, only the 500. Yep, it would work. Because, the thing is, the way it's set up, the only places forces can be applied are at the joints. So that's what determines whether it can be a truss or not. Any other questions? Yes, because that fixed joint, remember, the loads applied by a fixed joint are an unknown force vector and then a couple. And so that couple is what causes the problem. Sure. Okay, so I do think it can be helpful to remember this two force member simplification though, because there are problems where you might not want to treat the whole thing as a truss, but you can use that for a body or two. So let me show how that works. So let's say, how do I want to do this? Okay, so let's say we have a pin joint with the ground. And then I'm going to make this an equilateral triangle again. And a roller over here. Nope. Let's make this a pin joint and then. Okay, so now this thing can support itself without a third member. And let's say that there's a force here of 200 newtons. And let's say that these are two different materials. So this one we'll say has a significant mass of 10 kilograms. This one's something else. We're going to neglect the weight there. Okay. So how are we going to solve this? Again, think of each of these as being 1 meter long, and that's an equilateral triangle. And let's call this member 1, member 2, joints A, B, and C. So how do you want to approach this? I mean, really probably approaching it any other way besides just doing the full problem, just sucking it up and doing it is probably over, trying to be a little too cute. But what you could do here is, since we're neglecting the weight of this one, and it has pin joints here and here, this is going to be represented as a two-force member. Okay, so we can treat this as if it was just one of those cables that can produce tension or compression. And then the only rigid body we have to isolate is member 2. Okay, and that's going to save us some equations. Everybody with me on that? I don't really recommend this, but if you want to feel clever, you can do this sometimes. I like to feel clever sometimes, so I do it. Okay, so free body diagram of body 2. We have this force RC from the pin joint with the ground. We have the force F on, I'm going to call it F on 2 by 1. Is that what I'm going to do? No, that's not what I'm going to do. I'm going to treat this. So we're going to treat this member one like it's a cable. So this is just going to be a force like this, and I'll call that F1. And then we also have that 200 Newton force here. And then the weight force down is 98.1. Okay, so first RC, I guess I'll put the about point down here at C. So the row vector is 0. Force vector is RCX, RCY. Cross product is 0. Then the weight force, that's at negative 0.25. Positive 0.433, and the weight force is 0, negative 98.1. So the cross product is positive 24.525. And then up at the top, we have these two forces. So first the 200, that has a row vector of negative 0.5, positive 0.866. The force is 200, 0. And so that's negative 173.2, I think. And then last is that force F1, that's like the cable tension coming from member 1. That is the same row vector. That force vector is negative 0.5 F1, negative 0.866 F1. And so the cross product is 0.433 F1 plus point, so I think that's 0.866 F1. Okay, so our equations are RCX minus 0.5 F1 is equal to negative 200. And then RCY minus 0.866 F1 is equal to positive 98.1. And then 0.866 F1 is equal to 148.675. And then you could solve that. I mean, that's 3 equations for 3 variables. F1 is equal to 172 newtons, basically. RCY is, I think, positive 246.8 about, and RCX I think is negative 125. Does that make sense? RC. Yeah. And so what was the benefit of doing that? Well, the idea was we noticed that one of those two members was a 2-force member. And so we treated that like one of these positive negative cables. And that let us solve this problem with 3 variables and 3 equations. How many would it have been if we had done the full, treated both of those as rigid bodies? 6 and 6, you know. So it cut down the work a little bit. But it's my strong feeling that you'll never be in a research or professional environment where how well you do your job is going to be determined by how fast you can do a hand calculation. You know what I mean? If you're working in a place where they're relying on fast hand calculations to get correct answers, that's a place that I don't think is going to be around very long, you know? Yeah, so yes, to me, I say just do the full thing, be careful, take your time, get it right, you know, but this is a way to cut some corners. The reason that this used to be very important is that there didn't used to be calculators and programs and stuff that would solve big systems of equations and do cross products for you and all that kind of stuff. So everything kind of had to be done by hand. And you can imagine if you're doing stuff by hand, cutting the number of equations down by a factor of 3 is amazing, you know, and worth cutting out a lot of, you know, making a lot of approximations and assumptions for. But I don't think that's really the case anymore. And so that's why this isn't really the way that I like to present this stuff. I've always found too, like from when I first started teaching this class, like people, and I guess it was when I taught D-form, that people would come back and they'd kind of remember how to do trusses, but they wouldn't remember when it applied, you know, which really is kind of the most important thing about it. Like if you're sort of randomly applying some method to something where it doesn't fit, that's a big problem. So that's sort of my justification for why this isn't the way that I go. Yeah.
Was there a second simplification that you mentioned?
It's really just a little bit less general version of what I do. It's very similar to what I do, but the way that it's taught in books also keeps you from having more than 2 members meet at a joint. So basically, like including the thing with the subscripts, the force on 1 by 2, and then also what's the other thing? So those subscripts. I'm blanking right now. But there are two things that we do that sort of extend it so you can use it for anything. If you just follow the approach that they use, I know what I was going to say. So it's the subscript thing, and also then that thing about choosing like a base body at each joint. You know, those 2 things together let any kind of structure fit into that framework. Yep.
mentioned like large scale project, parsed, some sections to treat as trusses,
Mhm.
and would cut down on the number of proximate.
Yeah.
Would that change the margin of error in the final calculation?
It would, I mean, if you're neglecting weights versus including weights, that's something that would do it. Oh, you're talking about like the sort of the round off error in the computation itself. I have never had a problem with that. I don't know if you're doing, let me see if I can think that through. I really don't think that is usually a problem, like a problem you think about very much when you're solving big systems of linear equations. Maybe a big systems of nonlinear equations, but then you'd have to, it wouldn't, this is always linear, and you'd have to use a different approach than reduced row echelon form anyways.
Yeah. And so when like, back then, or like when these calculations are done, I'll form the question better and ask them.
Yeah, sure. Okay. All right, well, that's it. So see you Wednesday. No, I just had Alora do that so that I could make sure I got the right answers when I did it at home. Yeah.
Like I asked an email.
Yeah.
Like specifically what sections these are really.
Yeah. No, I don't want to do that.
Okay, that's fair.
Yeah.
I understand completely.
Okay. I think that's sort of the most important thing about.
Are you aware that the like proportions on number 7 on structures are like really, really bad?
No, on the
Like really bad.
the proportions.
Yeah.
Let me look. Now I'm so interested to find out.
So the way the numbers are, so here to here is 1.5.
Oh.
Right? Then here to here is 1.4.
Yes, I do remember that one's pretty out of whack.
Yeah, and then this is 2, and
Yes.
then this is 1.5.
I do. Yes, that probably is something I should fix at some point.
The numbers are nice.
Okay. Yeah, thanks. It's there now.
Oh, is there no?
Yes.
Okay.
I don't think so.
Oh, I'm going to ask you, do you have a cheat or something like that, or?
It's on there. All the equations you need are on the
So
test.
it's like, a separate sheet where you have a table.
Ooh, table. I'm glad you mentioned that because I have to put the table in there. Okay, well, I'm bringing that over right
So is
now.
it like, are you gonna like print out like a copy table?
No, just the one page you need.
Oh, okay.
Yep.
All right. Thank you.
Yep.
Oh, yeah, the refrigeration table solutions are into that in there for the daily still, unless they're not supposed to be posted.
Oh, okay. I'll do some of those in class.
Okay.